robotics, graphics, and computer vision. This is our last seminar of the year, and we are really happy to have Stefan Leutenegger from Imperial College London give the seminar. Stefan has a bachelor's degree, a master's degree, and a PhD from ETH in Zurich. He finished his PhD in 2014. And he's currently associate professor in robotics at the Department of Computing at Imperial College. He leads the Smart Robotics Lab there. He also collaborates with the Dyson Robotics Lab. And because he has still more free time, he co-founded SlamCore, which is a spin-off company that is dedicated to commercialization of software and hardware, I guess, for localization and mapping for robots and drones. Stefan is working in one of the top research labs in the world in SLAM, that for which this is one of the reasons why we are extremely happy that he can give his talk today. Stefan, thank you for accepting our invitation, and you can start whenever you're ready.
Okay, yeah, I mean, thank you very much, Jose, and it's a great pleasure to be here and give this talk at another great epicenter of SLAM, I would say. So yeah, let me talk a little bit about spatial AI for mobile robots. So here's just a quick example of why spatial AI is important for mobile robots, and this is in fact an application that we put together at the lab, at the Smart Robotics Lab, a couple of years ago now, for a competition. Some of you may have followed that competition in Abu Dhabi 2017, where essentially the goal was to really have a fully autonomous drone that has the task to then find a moving vehicle on the ground, approach it, and land on it. And it really had to be all fully autonomously. And so here's the kind of prototype drone that we put together. This is all off-the-shelf components. There's some cameras on here, actually a visual inertial RGBD camera. Also a downward-looking camera, as you can see on the bottom right here, and then an onboard processor, this Intel NUC over there. So it had to be all done on board here. And what we're doing here is to be completely autonomous, also to be able to do this indoors if we wanted to, or in GPS-denied environments. We were really only relying on visual inertial SLAM, and then had a model predictive controller on top, and this downward-looking fisheye camera here would detect and track the target on the ground, and then approach and land on it. The tricky bit, though, is to not just do that once, but to really be able to do that in all possible circumstances. So as you can see here, these are successive experiments in different lighting conditions and in different wind conditions, even different speeds of this ground vehicle. So I guess, getting it to work really robustly in this kind of setting, that's a real challenge. So that's just been an introductory example of what a fully autonomous robot does. I think, of course, there are a lot of examples of things that are already working in the domain of autonomous robots, and things that we hope that will be working one day or another. So here's just a little bit of an overview of the kind of robotics applications that we would find, or that we would find people talk about, and I colored them as to how I believe how well they currently work, right? And I grouped them a little bit into two axes, where we're looking both at complexity of tasks. So we have the kind of very open-ended complex tasks on the right, and very narrowly, very clearly specified tasks on the left. And also the environment. We have the very open-ended environment on top, and very controlled, very specific environments on the bottom. And as you can see, really, the big difference here is that the things that tend to work, they are on the left and on the bottom, right? So once you're going to try and do very open-ended environments and kind of complex tasks, things like household robots and autonomous driving anywhere on Earth using the current infrastructure, then these are still, I think, quite a far way off. Whereas if you look at this example of the drone I just shown before, this is really a quite narrowly specified task and a sort of only moderately open-ended environment. And so these are the kind of things that tend to work quite well at the moment. So it's really quite obvious, I think, in this one that actually the perception of the environment, the spatial AI that I'm talking about, really plays a really important role in this whole thing if we're trying to make these things work in the real world. So just a bit of an overview. So here's is the kind of traditional way of how roboticists have been framing the problem of doing autonomous mobile robotics, right? And I'm sure you will have seen similar graphs in graphics in your courses, where you have these kind of modules. You do perception, you do some state estimation, mapping, SLAM, these kind of things, and then you feed that result into some kind of planning. Ultimately, you do motion control, and the whole cycle kind of repeats itself. So this is the kind of classic modular way of doing it. It has definitely a lot of advantages. You can really introspect as a user what's going on. You have the same kind of representations and knowledge that's being used, so it's kind of easy to see what's going on. But at the same time, I would say the big difficulty, and perhaps why all of these applications don't really quite work as well, at least the ones that are read in the previous slide, is really because there are gaps in between these modules, and especially between the sort of sensing side and the more abstract planning and control side on the right, where, you know, if you have your state estimate that's coming from the SLAM system or so, it's just not quite robust and good enough, not expressive enough, then, you know, you've already lost. You have the thing's already broken. It can only do so and so much, and it will only be so and so robust. And of course, at the same time, we have now kind of completely new paradigms of trying to do things in a much more end-to-end kind of way, where people are trying to do end-to-end deep reinforcement learning, for instance, where you can directly map sensor inputs to actions, which, you know, kind of immediately gets rid of this kind of gap. So that's nice. You have to perhaps do less handcrafting of these modules and connecting these modules. But at the same time, you somewhat lose any of the kind of introspections, possibilities, and perhaps some guarantees of how this thing is going to work. And also, I would say, while it's really quite impressive what these kind of systems can do for, again, relatively narrowly specified tasks, it is difficult to scale it to a more sort of open-ended spectrum of tasks that you might want to do in robotics. Also, you know, just because at some point doing very general things would lead to an almost unlimited amount of data that you would need to train all of these different things that you might ever want to do. So it's becoming a bit of a question of data efficiency at the moment. So what I would argue is that we will probably see, and that's what I will be talking about mostly in this talk, we'll probably see a lot of the kind of advantages from deep learning, from machine learning, entering more traditional modular type systems to bring these things together in order to be more data efficient and to have more ways of introspecting this thing to see what's going on, and also to leverage previous knowledge and models that we already have. So over the years, I mean, these are the sort of things that I've been involved with doing when I'm talking about spatial AI. I think it helps to see maybe things as a sort of system of levels, where a very basic one is just mostly focused about position orientation estimation, just the kind of motion tracking that you really need in order to control a robot. Things like sparse visual inertial SLAM, and of course the labs in Zaragoza are also very much concerned with these kind of things with ORB SLAM. The system that I've been developing is named OQUIS. I won't really talk about it, but this is the kind of thing that was actually running in the example that I've shown on the slides before. So this is really focused on robust and accurate motion tracking. And on top of that, once you want to do more actual interaction with the real world environment that is a bit more complex than perhaps just, you know, a flat ground where you can make some assumptions, then you will want some kind of dense mapping probably. You want to have some denser understanding of the environment. The next level then is concerned with a semantic understanding. So again, this is now really where you can start to leverage deep neural networks and put them together with the 3D understanding to really get this notion of what is a bed in here, what is the floor, what is the wall, which would really allow the robot to do more advanced planning and also more advanced interaction with the user. A user can say, for instance, to a vacuum cleaner robot, go clean the floor underneath the bed, right? And you really need this level of semantic understanding in order to do anything like that. And perhaps one level up here in the pyramid, we see things like object level and dynamic maps. This is also something I'll be talking about a little bit in just a bit, where you really try to organize the map not just into a kind of rigid geometry, but to break it down into individual objects, individual geometries, where you're also able to actually track and see what's going on when these are moving around. And of course, Berta, who has recently defended her work, that's very much also situated in this kind of space. So as I said, I will mostly talk a little bit about dense mapping and object level and dynamic maps. But perhaps to start, here's also an overview of SlamCore that was also already mentioned by Jose just before, where we're following really quite a similar approach, just with a focus on commercializing these types of things, where we have the different levels. We have the level of visual inertial motion tracking, and then trying to build on top of that dense mapping for motion planning, including even some scene understanding on top of it. So I won't talk much about this, but of course here the focus is on actually commercializing these things. So quickly skip through this in just of time. Okay, so let's now start, however, with just seeing a little bit what we're actually trying to do when we're talking about SLAM, what it really is that we're trying to do. And I'm well aware that you will probably have heard some of that before, but it's perhaps a good reminder. So in this ideal setting of trying to do probabilistic SLAM, we have measurements, let's call the measurement set, and we interpret these as samples from a distribution, P of Z given X, where X are all the variables that we're trying to actually find. So that might be robot states plus usually some form of a map. And what we're trying to do now is really something that actually sounds quite clean and nice. It's trying to find the values for X that best explain these measurements. And maybe we have some prior knowledge as well, and then there's a modification from maximum likelihood estimation to maximum a posteriori estimation. So that sounds like the right thing to do somehow intuitively, but then actually there's still a lot of choices that we have to do, and I would argue that this is actually where the research happens, right? So we have to decide for a representation, very important. How do we actually represent the state, and maybe even more importantly, that map? And then we have to do all the models. We have to model this likelihood function, this whole probabilistic modeling. Maybe we have some prior knowledge. Maybe we have some regularizers or so. And then we choose all kinds of approximations, because typically these kind of straightforward problems, they become ever-growing optimization problems that are not well suited for real-time robotics. So we'll probably do some way of approximations, doing some filtering or whatever. And also, not to underestimate, there are always ways that are needed to bootstrap the whole problem, to associate data, to initialize. Very important. We focus in our papers, I think, a lot on the estimator formulation and so on, and rightly so. But actually, whether or not the system really works can really also be just down to the way you bootstrap things, associate data, and initialize. And so actually in pretty much all of these, again, we can use some deep learning to help the process, even though, of course, these methods have been previously devised a long way before we were starting to bring machine learning into this whole game here. Right. So just a little bit now on DenSLAM, because unfortunately in DenSLAM, very often we find ourselves in a position where we cannot do this ideal thing that I just explained, where you jointly estimate all of these variables, the map and the pose of the robot. Very often we have to simplify the problem and separate the tracking part from the mapping part. So we usually assume that there is a sort of fixed geometry in the world, it's denoted here as the black line, the dense geometry, and then we do a step of tracking where we just estimate the pose of the camera or the robot, And then afterwards, we do a step of map integration. So we may have as an input an RGBD camera with a more or less dense depth map if you're lucky. And then, of course, the RGB image on the top right here. And we can do things like ICP-based tracking, where basically we just project out the 3D points that are measured in a live depth frame, and we are computing by projective association. We're finding the corresponding pixels to a keyframe, for instance, and we're trying to minimize this distance, let's say usually a normal distance to this dense surface that we have in our map representation. And then this leads us this classic per pixel cost function that we can minimize in a nonlinear least squares sense and actually optimize for the best pose, the best camera or robot pose that brings the live frame into alignment with the 3D geometry. We can augment this formulation with also using the color in a direct photometric alignment, where again through projective data association we can find the corresponding pixels in a keyframe and a live frame, and we can just use the color difference here per pixel, sum all the color differences, and minimize that. We can even combine the two things and minimize them jointly. Right. So that's the classic kind of dense tracking formulation that you can adopt. And here's an example of something that we put together a couple of years ago already now, which is elastic fusion, which some of you might have already seen. Let's just hope this is actually coming up. Okay, here we go. Pretty much doing exactly what I've just explained. So you represent, in this case, the world as a collection of basically millions of circles. These are basically points that we color them here also. They have a color. The camera is moving around. You alternate this step of tracking the motion and mapping the world, putting new stuff, new ones of these points into the world. And of course, you're accumulating drift. And now that's where the trick now happens. When you're accumulating drift, you have to somehow resolve this issue. And you have just seen an example of that before, where basically you return back to a place you've been before. And you have two instances of the map that are not exactly in alignment. So you should see that happening just here. Sorry, the video is somehow being a bit slow. Okay, so you see two instances of the map, and what we do here is we identify that they can be brought into alignment, the old part and the new part of the map, and we bring it into alignment. But now, rather than doing some kind of post-graph optimization to bring these things into alignment, in fact, what we do here in this example is we place a graph onto the dense geometry. So this is like a volumetric deformation that we then solve for to deform the whole map, the whole world effectively, to resolve this inconsistency that you will have seen. Okay, so I think it's just going to show a little bit more details about that. I apologize if the video is not entirely, I think it's stopping in between a bit. I don't know why. Okay, so it's just happening here again, right? You see two instances of the map are being created, and again, by basically ICP alignment, we find how they can be brought into alignment, and then we solve this deformation graph that brings everything into alignment, that brings the whole map into alignment. So this is now the kind of thing that you have to do, because we cannot a priori, solve all of this jointly. We cannot optimize for practical reasons the whole map, like all the 3D positions of all of these millions of surface elements and all of the poses where the robot is being jointly. That's just not practical in an online system. So we actually use this graph instead to represent the environment in that step. And that's a quite sparse graph where, rather than solving for millions of points, you're now solving only for a couple of hundreds of variables that can easily be done actually even on the CPU. All right, good. Well, I'll leave it at this with elastic fusion. So that's just been an illustrative example of a dense SLAM system where we have deviated somewhat from the ideal probabilistic formulation and then had to do a little bit of a hack in some sense to to bring things into consistency again. Okay, so here just a quick example. So you have the current part of the map that's being colored here, and then the old part of the map is kind of getting grayed out. So there's basically a timestamp on all of these surface elements, and then when it's getting too old, we don't trust it anymore, we don't track from it anymore, and we don't map into it anymore. Instead, we are trying to bring the colored and the grayed out part of the map into alignment when there is a loop closure that's actually detected. Okay, all right. So here's another example, though, how we have tried a bit more recently to tackle this problem in dense SLAM, where you cannot solve for the very rich geometry and the poses jointly. And in fact, in this example here, we are also tackling the slightly more challenging problem of monocular dense SLAM. And now, instead of representing the scene with sort of 3D surface elements, we are representing it with keyframes where we store depth. And also, rather than just storing every single depth separately, what we're trying to learn in this work, Code SLAM, is actually, well, as I just said, we are using deep learning to learn a lower dimensional representation of that keyframe depth map to represent the environment. So basically, there is a training step here that is happening where we're using synthetic data, where we're trying to learn a sort of autoencoder, a conditional autoencoder, though, that lets us reconstruct at this point the ground truth input depth as well as possible, together with actually an uncertainty map. But importantly, this learning here is conditioned on the input image. So we're not trying to learn a very generic code representation of any kind of scene. We are making it very specific to what is also seen in the RGB image, right? So that you learn features that then are coming only from the input image, the RGB image, and they go into both the encoder part and the decoder part of that kind of conditional autoencoder. Because the trick with this system is that at deployment time, we don't have input depth anymore, right? I said this was a monocular SLAM system where you don't have a depth map input. So now you've just got the input image, and you can still have a reconstruction of your depth, which is basically determined by a code, the kind of code representation that we previously learned, and where the decoder now is conditioned on the input image. The interesting thing about this is that now we have learned this low-dimensional code representation that serves as our representation for the world, for the scene. So you might have something like 32 variables now that actually encode the whole depth map, which is in the order of hundreds of thousands of depth values that would otherwise not be suitable to optimize for directly, because now you can actually optimize the code. So the idea is that we can now jointly optimize the code in these keyframes together with the poses of how the camera has moved around. And this allows us to go back into what is more this kind of ideal probabilistic formulation of SLAM, right? So we said ideally we would want to jointly solve for the geometry and the poses, and this is exactly what we can do, except that now the geometry is represented by these low-dimensional codes that we have learned. So we can now run this kind of dense bundle adjustment where we're using as error terms, again, the photometric error that I have previously outlined. So we're trying to get color consistency between these viewpoints, and now we can solve for geometry and poses jointly. Okay, so here's just some example of how this actually works in practice. Kind of interesting, this is now real-world imagery, whereas we have trained the autoencoder just from synthetic images. And it still works. It's not perfect, obviously, as you can see. The geometry is perhaps a little bit overly smooth and so on, but you may see that a robot could use this kind of representation to just kind of navigate around and not bump into things. Again, note that this is a monocular SLAM system. There's no depth map that is actually coming from a sensor. Okay, so that was one way of bringing learning into SLAM. I want to just briefly now talk about some more recent work as well that we've done, which is yet using a different representation of the environment. There's always this question of what is the right representation of the environment if you want to do robotics. And at the moment, at least, I actually think that some form of volumetric representation is really quite useful. So we have been working quite a lot recently with such volumetric representations. And particularly with both truncated sign distance fields as well as occupancy maps that are represented in log odds, which both have this interesting characteristics that surfaces are then only represented implicitly as a zero crossing of a function that is defined in the whole volume, in the whole 3D space. So you can see that here, again, the dense geometry now being where this function crosses 0. And of course, now you can do that sort of more efficiently or less efficiently, how to encode this kind of function. Naively, you can just allocate the dense 3D volume, and just for every voxel in the 3D volume, you can store this value. But that's really not very efficient. So you run out of memory very, very soon. So what people usually do, including us, is to limit the representation of this function to a sort of band around the surface, and to also use octrees to represent that. So you can take basically a large cube and you subdivide it into its 8 children recursively, and ultimately you have a densely allocated voxel block there that you can see, where we can now actually store physically these TSDF or log odds occupancy values. And perhaps what is more interesting about this representation is, I think, that this allows very naturally for the integration with this idea of adaptive resolution mapping. So when you are actually close to something that you want to map or that you want to track from, you will want to have high resolution, right? And when you're further away, this is just how the camera works. You don't really need these details. It's a bit like you're zooming in and out of Google Maps, right? You only need the details when you're zooming in close, and if zooming out further, you don't need them, and you can't have them for efficiency reasons. So what we want here is to have this multi-resolution representation of, well, effectively in this case, the TSDF values or occupancy values. That, you know, it's just that they are represented at different scales. So the tricky bit now is to keep these things consistent. So we want the average of the 8 children to be the value that is actually stored in the parent node. So we have this kind of scheme to keep these things consistent. But now this allows us to access at a desired level of resolution. So you can determined by how far away you are from a certain place in space, you can now select the resolution that is suitable. It's visualized on the right as well, where you see it's kind of a mini frustum of 1 pixel basically from a camera that now allows you to select the appropriate resolution as this mini frustum, of course, grows in space with increasing distance from the camera. And this allows really to avoid aliasing artifacts and to also speed up the mapping process. So here's an example of what that looks like. This is basically a straightforward adaptation, again, of what is Kinect Fusion, which does ICP-based camera tracking, as I explained before, and then you integrate this TSDF function by basically some form of weighted averaging, and we do the scale selection here, where this is the same color coding as before. The green one is basically the finest resolution, then the red one is slightly coarser resolution as being selected, and the blue one is the coarsest one. Okay, and on the right, you actually see also a color fusion of the whole thing. So you can use this exact same idea of adaptive resolution mapping also for colors. So you can equivalently store also color values, not just TSDF values, in this kind of multi-resolution way. So here's just a couple of examples here again. So this is really the difference that you get, and you can see the details in this view here is when we use the adaptive resolution approach, and you can see all of these artifacts that happen if you don't do that. So here the camera was kind of moved in and out of the scene, and you can really see the benefit in terms of quality of the adaptive resolution approach that avoids that because it avoids aliasing. So you can think of it as integrating. Basically, you're missing a lot of voxels if you just always by default just select the finest resolution. So that maybe something I should have said before. The comparison here is using the same resolution. It's just using constantly the finest resolution everywhere. Whereas in our adaptive resolution, you just automatically select the right resolution. Okay, so that's the quality of things, but also in terms of computation time, you actually gain a lot from this kind of thinking. So you can see the computation times here in comparison with some state-of-the-art stuff that is actually significantly faster, because you don't have to touch the memory at the finest resolution, I mean, all the time. And also in terms of trajectory error, when you do ICP-based tracking, of course, then because you have a finer representation of the environment, then your tracking also improves, so certainly doesn't deteriorate. Okay, so here's just an example how we took this a little bit further, and I'll skip through it a little bit, but that's newer work where we extended the multi-resolution, the adaptive resolution thinking also to occupancy mapping. So the difference being that here you now really also encode the whole free space in this kind of multi-resolution way. And the nice thing that this allows you to do is that in free space where there's nothing happening, you can really just have big blocks that you just label as free, and you don't have to represent any details underneath, but you can still represent all of the details at the walls where things are actually happening. And what this allows us to do now is to do really quite fast motion planning, because you can do free space queries in this very efficient adaptive resolution way. So if you are at the place in the middle of a room where you have to only allocate a big volumetric block, then you can immediately know that this is free, and it's only when you're close to obstacles that you have to traverse further down the tree and figure out where there is actually some potential obstacles. And so here's just a bit of an illustration as well as to how we are now, I'll just stop that, really allocating the volume to the detail that is necessary. So you can see this is just one depth view at the wall, and there is this little pole in front of the wall. And so if you want to do occupancy mapping really correctly, you have to represent the boundaries, the occlusion boundaries, as well as the frustum boundaries, really at the kind of higher resolution. So we select the resolution according to the resolution selection that I presented correctly at these boundaries. And at the same time, in the free space, you can really afford to go with very coarse representation of that free space. Okay. What it didn't do, the system that I've just shown, is use any learning, right? So that's in many ways a very traditional thing to do occupancy mapping like that. It's just that we brought it to higher resolutions and this multi-resolution, adaptive resolution thinking. But what we've done in this work that I just want to very briefly show is to bring in some learning in actually filling the holes, the gaps that you will very often find when you're using a depth camera, right? So in a depth camera, you have stuff that's too far away, maybe reflections and some occlusion boundaries where you don't have any depth values. And what we do in this one here, again, with this idea of bringing in some level of deep learning, is we brought in a depth completion network and use otherwise the same adaptive resolution occupancy mapping framework. But we now have this depth completion network that takes as an input, as you can see here, an incomplete raw depth map together with the RGB. And from that, we predict a learned completion as well as also an uncertainty map. And so that's an important point here, that we also can learn the uncertainty. This is using straightforward negative likelihood, where you also predict by the network the uncertainty, and then you have a direct way of actually using that these uncertain depth predictions into the occupancy mapping framework. So you can just replace that likelihood model by the learned predictions of the uncertainties. And here you can see the benefits of this system. And so if you just do raw in the middle, raw occupancy mapping, you get a lot of gaps, right? Just because, again, there's a lot of depth points that are actually missing. So the ground truth would be a reconstruction where you didn't have any gaps. This is in synthetic data set, this evaluation. You don't have any gaps if you use the ground truth depth maps. So you get a very nice free space map of the whole space. And if you use more realistic type depth, you get a much sparser one. And of course, this can be a real problem if you want to do any motion planning. If you want to fly a drone around here, for instance, you have a lot of unknown space now that, to be safe, you're not allowed to do any planning into, and you will be very restricted in your movements because of that. And on the right, you see our completed map. So yeah, you don't have all the details of which you might actually want to know about, but you perhaps just know enough about where there is more likely going to be free space, especially in the area just surrounding the robot. So that will allow you to do much more straightforward planning and exploration, for instance, as opposed to having to always navigate around all of these unknown spaces otherwise. Okay, so quite a useful adaptation, I think, again, where you can use a straightforward integration of deep learning into a quite traditional mapping system. Okay, so I'll more or less skip through that, but we can actually also use that at quite large-scale mapping. So this is some collaboration with Oxford and Maurice Fallon's group, where we do LiDAR-based mapping, and we can use the same kind of multi-resolution approach to do that. And in fact, we can also then extend that to quite large-scale sub-mapping approaches and doing reconstructions on the ground here to do planning inside these quite large-scale environments. I'll skip through that in the interest of time, because I wanted to also show you just a little bit the sort of higher levels, or the highest levels that we are currently tackling of spatial AI, where we are now decomposing the scene not just into a rigid kind of static map, but we are trying to decompose it into individual objects. So in this work, Fusion++, we're using straightforward neural network, mask-car CNN, basically, to bootstrap this process of then starting to map individual objects. So you can see here, on the right is the reconstruction, on the left you see the input. So we now reconstruct per object maps. So these are detected by mask-car CNN, and then we place new objects when they are detected. And we are just basically using the same kind of volumetric mapping formulation to reconstruct them. And what this allows us to do is to build a kind of graph of camera and object observations, as well as camera-to-camera edges, which are formed by the probabilistic analysis of exactly the ICP error and the photometric error that I've introduced. So we can really build this probabilistic graph of this relative pose information. And what we are left with is actually an optimizable graph, which I think is very nice here. This allows you to then, once you have a loop closure, to resolve inconsistencies differently than in elastic fusion in this kind of object-based way, right? So you can now just optimize the 60 poses of all of these individual objects and of the cameras that are observing these individual objects, and everything will be brought into consistency, into alignment, and you have this kind of object map. So again, it was in some way, it's a kind of reparameterization of the problem. So you now decompose the scene into rigid objects so that you can actually optimize a small subset of variables, again, the 60 poses of these objects, jointly again. So you can go back to this idea of jointly optimizing things with the camera poses. All right, but finally also, the kind of same approach here that we have adopted also for moving objects. So again, we're using mask-car CNN to bootstrap, basically putting all of these objects into individual maps. And then they can just move in this case as well. So we're tracking the camera with respect to what we identify as being the fixed map. And we're using the same, again, ICP and photometric error per pixel to identify which of the objects are consistent with the static world assumption and which ones are not. And then those who are not consistent, we can use, again, the same formulation of ICP and photometric error to actually just separately track the moving objects. So there's no a priori information here. I think that's important to note. There's no a priori information about which objects will be moving and which not. We really determine that on the fly when we are actually observing them, whether or not these objects are moving. So there's no, I just emphasize it again, there's no information here available about the camera motion or about the 3D geometry of the world or the individual object. So it's kind of the hardest thing that you can do, but you know, it works somewhat. It's not perfect, so you can see here perhaps some artifacts, right? So it can deal with a number of different objects, but you will still have some kind of ghosting artifacts and so on. So definitely still some work that's left to be done in this space. All right. I don't know if do I have like 5 more minutes, Jose?
Yes, absolutely.
Okay, great. So then I wanted to just very briefly show some applications of actual robots. In fact, drones. I mean, I've shown you one example already. The idea is, of course, to now leverage this level of spatial AI in actual robotics. And so basically on top of this slide here, you can see exactly what I've shown initially, where now you have a drone that's leveraging visual inertial SLAM, and then there's a controller that controls it. In this case, it's actually a linear model predictive control, and then you have this kind of internal PD controller that controls the attitude. So it's this kind of cascaded control scheme that we were using. More recently, we were moving towards using directly the nonlinear dynamics of the system. Now, I know this is kind of going beyond computer vision, but I think it's still somewhat interesting to show. So I wanted to show you some moving drones. Basically, the idea being that rather than representing these kind of closed loop dynamics, PD controlled dynamics, we just directly try to identify a model for the full physics-based nonlinear dynamics of a drone. And then we control effectively the individual rotors of the drone directly determined by the controller. So the way this works is that you run some nonlinear least squares model identification. This is really just what physics tells us here. You use Newton-Euler rigid body dynamics. And then there are a couple of parameters here like the mass and inertia and thrust components and so on that you can identify by just analyzing a sequence that you recorded in a motion tracking system. And once you have that, you can now solve then online the nonlinear model predictive controller optimization problem by basically finding the optimal control sequence within a finite horizon that minimizes, in this case here, position and yaw deviation from a nominal trajectory that you want to follow. And you get really quite nice and aggressive behaviors here, so I just want to briefly show you that. So by basically now telling the drone to do a set point change in position and orientation, the controller will just automatically determine this optimal control sequence to do this kind of really quite aggressive maneuver. And you can see on the bottom right, this is actually what the model predictive controller thinks is going to happen within that horizon. And as I hope I can convince you, this really looks quite realistic. So after you have identified this model, this is really not learning based anymore, right? I mean, there's an element of learning, perhaps, if you will, of these model parameters. But once you have identified them, you have a very, very well generalizing model that lets you do really quite interesting stuff, and importantly stuff that you haven't seen before. So I've just shown also some examples of a drone upside down, right? So these haven't been seen before, but because you have a nicely identified model, you can actually do that very automatically. The controller will just do that. And I'll just stop that here, or let me show the next example. The other thing that we can do is we can actually switch off a motor, right? And we can use exactly the same controller formulation when there's one motor stopped to still control the drone. So you'll just have different limits that you impose on your model. Basically, there's no thrust, neither negative or positive thrust that can be generated by that motor, and the model predictive control will just automatically find the right thing to still save the drone when something like that happens. And in fact, in this case here, we can identify when a motor is being stopped. So we've kind of manually stopped the motor, but the drone doesn't know about it, and it has this scheme where, again, in a model-based way, using the same kind of model parameters that are identified, the drone can monitor the health state of the individual motors, and then it doesn't only actually have to react to motors that are stopped, but it has to first identify that the motor is stopping as well. Okay, so that was just an example. In the very end here, I'll show that again, that we run successive experiments where it would always correctly detect that the motor was stopped. It's quite important that you have really a 100% detection rate and a 100% precision, because otherwise you might be missing motors that are being stopped, or conversely you might be reacting to what you think is a failed motor, and neither of these things are good, right? In both of these cases you might actually have a crash. Right, final example, just to come back again a little bit towards spatial understanding as well. What we actually wanted to do is use these kind of drones to interact with the environment. So here we have a drone that is equipped with this delta arm. So the delta arm is individually controlled from the body of the drone, and we can get it to write something on a whiteboard by basically just changing slightly the objective function of that model predictive controller. So here we're doing 2D position control. So in the 2D plane of the whiteboard, we can do position control, which is quite accurate. And into the normal direction, we can have force control. And the rest is kind of being solved implicitly by the model predictive controller. So it will just maintain a constant force when it has to, and it will follow this 2D trajectory that we gave it. So that's an interesting scheme, I think. Again, it's just a relatively straightforward adaptation or extension of the previous controller formulation that we are using here. All right, and again, it's doing this thing several times in a row, not just once. We are not using, unfortunately, here yet any visual feedback or anything. So that's really clearly the next thing that we have to do. I would like to bring back the kind of spatial understanding I was initially talking about, to really make this drone do this thing all completely autonomously, in the sense that it would have to figure out itself where actually the whiteboard is, and it would have to completely rely on its own SLAM system. So here we're using a motion tracking system actually to do this. So these are clearly the next steps that we would like to do. And with that, I would like to end the talk. I will just leave these conclusions here. One thing I wanted to just briefly note is that in my new position at TU Munich, where I'm going to go in just over a month's time actually now, I will be looking for PhD students and postdoc to join me. So who knows, maybe there is some interest by any one of you there. And I'll leave it at this. Thank you very much.
Thank you, Stefan. This is really interesting stuff. We will start some time for questions. Whenever you need to leave, Stefan, then please tell us.
No, I have some time for some questions.
Okay, and I'd like to ask the students, if they have any questions, please mention that in the chat so that we can have an order. Beginning now. Yes, David, that's your question.
Hello, I guess that I will ask my question. Thank you for the talk. It was incredible, and it was really extensive for many topics. That was really nice. My question was focused on the part with the faulty motors.
Mm-hmm.
You can detect one faulty motor. Would this the limit of faulty motors that the system can cope with?
That's an excellent question. Yeah, I'll just maybe scroll back to the right slide. So as you can see, the approach that we followed here was to, let's see if hopefully I can show that, to monitor every motor individually. So we have a health variable that is being estimated. It's actually a kind of extended Kalman filter type formulation that is estimating, here we go, for every motor, right? So we have 6 motors, and for every one of them, it's monitoring the health. 1 would be healthy and 0 would be not working. So in principle, it can detect any number of failures here. Now, we haven't tried with too many, not least because, of course, at some point when you have too many motors that fail, it becomes impossible to control the drone as well, right? But in principle, what you could still do, at least if it's the right kind of motors that fail, you could do 2 as well, and you could still at least control the position and orientation except for the yaw angle of the drone, right? So if you had 2 that failed, you would get this drone that kind of spins along the yaw axis, but you could still actually control it and probably safely land it, but we haven't actually tried that. So we have some simulation results for that. But as for just the detection part, in principle, you should be able to detect any number of failures. Of course, I imagine it would get harder and harder once it's more than 1 that's actually storing, especially if it's more than 2. The argument here is, though, that it is quite unlikely that you have more than 1 failing, because the operational mode would be that once you have a failure, you would, in any case, bring the drone back to the safe landing, no matter what, as soon as possible, right? That's the idea. Okay.
Okay, thank you, David. More questions? Diego?
Yeah, thank you for the talk. I wanted to add something to this question. So I'm not very familiar with drones, so I don't know if this is a common problem. But also with this failure recovery thing, is it a common problem that maybe the motor is not that it stops completely spinning, but it spins like half as fast, or it's broken at the movement it makes is not what you really are telling it to do?
Yes, so actually, another good question. So that it would just only kind of turn at half speed or so is relatively unlikely with this kind of electronically commuted outrunner motors, I would say, although I'm also not a D-main expert. What it is more likely, though, and it's a good question, right, is that you might, for instance, have also a propeller that touched something, right? I mean, of course, you're trying to avoid that, especially us being experts in spatial AI. You would expect it doesn't fly into things. But, something might happen and half a blade, for instance, might be lost. Or it might become loose, right? If you haven't properly tightened it. Again, it's not something that should happen, but we have seen that in the past. And then you will get these kind of cases where you have a partial loss of power, not a full and not an instantaneous one. So what we are doing here is precisely because of that, we are monitoring this kind of health variable that in principle we can track it, right? We can track as how much thrust should it provide, how much does it provide, and then we just take a decision. So at some point we decide, okay, this is not healthy enough anymore, and we then basically turn it off completely, because at that point we think it's not safe enough to rely on this motor. Since we have the redundancy, we might as well switch it off and just go back and land in this case.
Okay, thank you very much.
Thank you, Diego. So actually I have a question, a couple, in fact. The first one is the work that you have done in SLAM is very impressive from the point of view of the dense, very detailed and very accurate models that you can come up with. I wonder, you did mention it briefly, But I wonder what your thoughts are on the issue of scaling. How large can you work to such detail in real time? Can I do a whole floor of a building? Can I do a whole building?
Yeah, so this is good questions, and I have to say that we haven't stressed these systems to the limits yet. So I can't give you, an exact number of where it stops. But I mean, in principle, the whole idea of this work is to actually have it scalable, right? So the octree representation, in principle, allows you to go to a large environment, as large as possible or as large as needed kind of environment. And the resolution selection helps you also managing it, because if you are far enough away from stuff, but you still see it, you don't have to touch the memory, right, at the finest resolution, but you only have to kind of, treat it at the right resolution, at the coarse resolution that is actually needed. So in some sense, the complexity shouldn't grow, because it's per pixel you will see kind of one volumetric element, right? More or less, that's the idea. No matter how large the map is, how far away stuff is, and that actually helps a lot with this kind of scalability argument. You still have, of course, practical difficulties, things like how do we deal with loop closures and so on. So I've just shown a little bit in this collaboration with Oxford, that then you have to start thinking of these kind of classic things of doing submaps. In this case, we're doing rigid submaps that you can still optimize with respect to one another, right? To bring things into alignment when you have loop closures. And that's also then where you will find some of the practical limitations, right? Of course, if you create this gigantic loop through a city and you have represented all of these individual maps, you will still have to then solve some form of graph optimization problem or so to bring all of these maps into alignment. But again, you don't really have to consider the finest resolution to do that. You can just, the finest resolution is just there ad hoc when you need it very locally, right? I think that's the idea, that these kind of finest details, they're just in there when you need them. This is actually, in practice, it's then implemented also in mapping in this kind of lazy evaluation scheme. So when you have new information that's coming in, that is only coming in at the higher resolution, then you can, it won't be propagated down to the lowest resolution. It will only when you actually need it, that this is then computed. So as long as you are kind of careful with your queries and use them locally, which is, I think, what robots do, right? I mean, you only have to query details locally when you're actually close to something. Then it should be quite scalable. So again, this is all a bit, hand wavy and theoretical, but I think the approach per se is what I believe in, because precisely this kind of capability of doing scalable mapping. Again, still a lot of challenges to resolve, of course, in practice.
Okay, and then if you want to apply these techniques to an agile flight like the drones, is that very challenging? Because of, so how agile can the sensor motion be before this breaks down?
Yeah, I mean, again, in principle, that's of course what we want to do, right? And we want to be agile in the sense that these models allow us very fast queries of free space. So we should be able to implement controllers in this very reactive way, and that directly considers the environment to a level of detail that is kind of fine, and that allows us to fly through fast, also through narrow passageways and so on. But of course, you still have the practical problem of things like motion blur and so on. So you're right to ask this question also from that perspective, right? I don't know the definite answer there, what we should do. Perhaps one way of doing it is gyro stabilization. I mean, this is something that we might be doing in
I see.
the future. But of course, I mean, you will run into issues there. I mean, for just the motion tracking part, at least, things like event cameras or so might also be a brilliant alternative. And of course, people like David Scaramuzza or so have been pioneering these kind of things. So you can also work with different sensors to mitigate it, right? So I think it will be probably a combination of finding the right sensors for the right task and adapting perhaps also the hardware to support these kind of tasks that you want to perform. Yeah, and then that's how hopefully we can make progress.
Okay. So finally, I understood that your talk was essentially advocating for the use of deep reinforcement learning techniques in most of the aspects of autonomous robotics. I wonder, so in the second part, except if I missed something, that the idea of the control for the aggressive flights sounded more classical control theory.
Absolutely.
So I wonder, do you think that there's also a place for deep reinforcement learning techniques in control?
Yes, so just to qualify that a little bit, I have actually so far not done any deep reinforcement learning in these kind of works that I've shown here at least, or anything published. It was more general also about deep learning, or that I was advocating to come into individual modules, and we have been using deep learning in the spatial AI side of things, as I've shown, right? But actually no deep reinforcement learning examples here. And I think there absolutely could be. But I also want to advocate a little bit the more classical approaches. So as you're right, so what I've shown is actually is a classical approach, right, with model predictive control. There is, if you will, this element of learning of the parameters, but that's, basically just a straightforward nonlinear least squares solution. So perhaps I shouldn't claim this is proper machine learning. But the nice thing about it is that you have a model that is 100% generalizing, right?
Right.
It's fully nonlinear, so there's no limits to, in any respect, that the model remains valid. So I think that's why I like that approach, because of course you could also learn it, right? Of course you could learn the model, or you could learn it even implicitly through some more end-to-end reinforcement learning or so. You could do all of these things, but they are data-hungry methods, and they will, not necessarily generalize to any kind of maneuvers that you might want to do. So just to emphasize that again, these maneuvers that we've done, they are just emerging directly out of the controller. They haven't been trained or specified in any way, right? They're just computed and solved for, and that's what I think is nice. But of course, the approach also has its limits. I mean, a drone in still air, in free flight, is kind of perfect for this kind of situation where you can actually use such a model. And I would argue that's why you should. But there are elements where that's no longer possible, right? If you wanted to do more complex stuff, if you want to get the drone to interact in a more, in a physical way with all kinds of more complex geometries and surfaces and things like that, or, even things like people as well, perhaps, or you might have wind and so on, and you might have, who knows, right? I mean, there will always be unmodeled and difficult or even impossible to model effects in robotics, and that's where I would advocate you absolutely should be using learning, right? I mean, that's where we have to also, in some sense.
So I have the general sense that machine learning is useful when you don't really know what to do.
Exactly.
And then it's a good thing to try, because it has proven that it works much better than anything that we had tried, just because in the problems that we don't really know very well, like perception, how to solve. But when we know more about solutions like in predictive control, then it sounds like there's less a need for incorporating these techniques, right?
I would 100% agree with that. I think you could still see that there is a need. For instance, the method is relatively expensive that we do, right?
Of course.
I mean, we run it in real time on board the drone here, but you will have limits in terms of prediction horizon, for instance. So if you wanted to do something with learning, in principle, it's possible to learn behaviors and so on that have perhaps a longer kind of strategic horizon than the kind of things that you see here. So again, that could be an argument for learning, to make it more efficient and also to ultimately have a longer term horizon in these kind of learned behaviors. So yeah, I think it's a quite nuanced answer to what I think is the right question to ask, right? But I mean, we have to keep asking ourselves, and I just think it's not very useful to say either we have to do only model-based stuff or only do learning. I think we have to really quite carefully think about what are the benefits of each one of them and how can we bring them together to really achieve the best.
Absolutely. Okay, I think Tomas had a question. Tomas Derriel, did you have a question? I saw that you raised your hand.
I have a question.
Go ahead.
Yeah, so thank you very much for the talk, Stefan. And I have a very, I don't know, maybe it's a very silly question. It's for the last part of the failure recovery system. So it's possible to extend this type of technique to more bigger objects like aeroplanes or helicopters. So what happens if the engine of that aeroplane is failing? So it's possible also to recover from that situation.
Yeah, so I mean, it's definitely not a stupid question. It's a very good question. I think in principle, yes. As long as you have some model available for how your actuators, affect the system dynamics, and this is kind of what you have to have in order to do model-based control. So you can also extend this. You could monitor things like ailerons or whatever control surfaces of actual airplanes, or you could think of actual rotors and so on. Of course, in practice, it becomes actually a really challenging problem when precisely you have other things than that are not models. So coming back a bit to the previous question, really, when you have like a wind gust or so, it can often be actually then ambiguous as to whether the wind gust is causing a certain behavior or whether it's a failed actuator, right? So basically, your wind gusts are unmodeled effects, and then you have these kind of ambiguities. So in practice, I mean, there's a huge body of work that will try to tackle these kind of problems. And I'm not claiming that these kind of things that we're trying to do here would work straight out of the box. So one thing that you could do, for instance, is that you could then have a hypothesis of perhaps something failed, but it might have been also a wind gust, and then you verify that hypothesis by specific actions, right? So you'll probably want to be a bit more conservative in your estimation. Oh yeah, this motor has actually something has failed here. You will want to validate it through actions and so on. And this is actually really what you would do as a pilot as well, right? If something kind of throws you around and you're finding yourself kind of upside down in a severe wind gust, I mean, this happens if you're flying out there, right? And you don't immediately conclude, I have lost all control and the airplane is broken, but you will try to recover the airplane. And while you're doing this recovery and while you're actuating, you will find out if it's actually a mechanical defect of some sorts, or if it wasn't perhaps just severe weather.
Okay, thank you.
Okay.
Okay, I see that Tian has his hand raised.
No, he already asked the question.
Oh, okay. I missed that, sorry. Okay.
And I don't know if maybe in the YouTube channel, sometimes there are questions. I don't know if Julio can see that in the YouTube channel.
No, there's no questions on YouTube, so.
Okay.
Yeah.
Okay, so any more questions?
I would like to ask a bit of an open question in relation to SLAM. I think that there is this discussion about whether to use visual inertial odometry or including the LiDAR and so on. Could you comment on this over the approaches you have commented?
Yeah, so you mean opinions of Elon Musk or so, for instance,
Yeah, maybe
regarding
not
what
too much Elon Musk, but in general, like
Yeah.
how could visual inertial odometry perform in comparison to more precise LiDAR methods?
Yeah, you know, I can't give a definite answer because a lot of these things they do depend on the environment that you're operating in, right? So visual inertial SLAM can be very, very accurate if you are close enough to well enough textured and well lit environments, right? It can work really, really amazingly well. We all know that. And at the same time, of course, LiDAR is the kind of state of the art in terms of robustness for all kinds of robotics, where maybe you don't have that, or where stuff is far away. I'm a quite pragmatic person. I think you have to choose the right sensor suite for the right task, and especially if I were to do autonomous driving at this point, I would probably also go with a LiDAR just because they work so well, and they solve a lot of problems that you have otherwise. But that's not to say that I think it's not possible to do it only with vision or let's say visual inertial plus wheel odometry, because clearly we as humans can also do it, right? So it's just perhaps harder and maybe more difficult to capture every possible difficult situation and so on. So again, I mean, I guess long story short is I'm mostly also an engineer, right? And I would argue to just use the right sensor for the right task. At the same time, of course, we do research on sort of both ends of the spectrum and try to push it as much as we can to see if we can make things like visual inertial SLAM as versatile as possible. Because clearly it's going to be cheaper, right? It's at the moment at least you can build really quite cheap and low power kind of solutions with it. So that's what we have been trying to do in research and also in the sort of SLAM core work. But yeah, there will remain use cases where I think it is the right thing to use a LiDAR or other sensors for that matter, right? I'm also arguing for the use of GPS if you have it. I mean, why not use it if it's there? So I think we have to be pragmatic if we are trying to really solve robotic applications as well as possible.
Okay, thank you very much.
All right. So I think that Tomas wanted to ask a question, but has connection problems. So I will ask the question.
Okay.
So he says, do the algorithms that you have explained improve their adaptability on outdoor scenarios in new environments, or is it still a work to do? So can you improve adaptability to new environments?
Yeah. So I'm not entirely sure I understand the question in terms of adaptability.
I'm here. I'm just making my interpretation here. I guess Tomas means, can you, as you go along, perform better because you are learning what the outdoor environment looks like? If there's many dynamic objects, can you improve the performance? If there's mostly static, if there's depending on the lighting conditions, can you learn as you go along and improve your performance?
Okay, I mean, maybe it's a question of online learning.
Right.
So that's an interesting aspect and something that, I think we haven't, I mean, the communities are not really doing much kind of at least real world work in this space. And in principle, of course, this is how it should be, right? Of course, as you're moving along, you should use your past experiences to basically train and update some of your learned parts and to become more versatile, more robust, really learn from new situations. I think we should do research along those lines, but it's hard, and I haven't done anything along those lines.
I agree that it's a big open question.
It's perhaps one of the biggest ones, right? How to do lifelong online kind of learning. I think we are very focused on things like data sets, and of course you will train with what you think is the right data for the right task, but how about if that task evolves over time? I mean, this is a natural thing to happen, and then you want to stay adaptable, and you want to use the experiences that you make to keep learning.
Yeah, that's right. Okay, maybe this is a good place to finish with this seminar. Stefan, I'd like to thank you again for accepting our invitation.
Thank you very much.
Good luck in Munich. I think that's a big win for Europe and a big loss for the UK. That's just how things
Totally
are.
agree.
Yeah. And hopefully that we will keep in touch. Thank you.
Yes, excellent, and thank you very much again for having me. It's been a real pleasure, and yeah, Merry Christmas to everyone as well. I guess that's coming up pretty soon too.
Yeah, thanks, Stefan. Same for you.
Thank you very much. Okay.
Okay, thank you.
Thank
Bye.
you. Bye, Stefan.
Bye.
Bye.